Section 6.3 is titled Exponential Functions. And so just like in Chapter 5, we looked at polynomial and rational functions and kind of focused on those. In Chapter 6, I think I mentioned this, we're going to be looking at a couple of specific types of functions. One of them is the exponential function. The other we'll get to later on this chapter is the logarithmic function. But first, let's see what the exponential function is, kind of what it looks like. And so kind of to kick this off, we're going to start out by looking at how to just evaluate some exponential expressions here. And so instructions say approximate each number using a calculator and express your answer rounded to 3 decimal places. So this is really a calculator exercise. This is 2 to the 1.4 power. And to do this on the calculator, it's really not too tricky at all. And so the way we're going to do that is you've got right below the clear button, you have a little up arrow, and that's your exponent button. And so to do 2 to the 1.4 power, you punch your base in, that's the 2. And then the little up arrow, depending on what kind of calculator you're using and how new the software is on it. Sometimes you'll hit the up arrow and it'll actually jump up to, you'll notice it kind of jumps up to where you can put in the exponent 1.4 and it actually writes it as an exponent. Now, a word of warning when you're doing this, if your calculator does work this way, it's not a bad habit to get into where once you type in the 1.4, always hit that right arrow key just to jump down out of that exponent. In this case, it wouldn't make a difference if you didn't do that, but if you were going to do something, an additional calculation, maybe adding something to that power, 2 to the 1.4 plus 7, it would make a difference. And I might show you an example of that here in a second, but just punching that in, hit enter, you get 2.639 for our answer there. So this is the 3 decimal places, 2.639. And then over here, 2 to the 1.41 power. So we want to type that in. Now you can help yourself out a little bit if you hit second, enter. What that does is it pulls up the last calculation you put in. So all we're going to do is just add this and make it a 1.41. So we can arrow over, hit the 1, drop back down out of that exponent, and hit enter. We get 2.657. And then notice 1c is 2.14, 2 to the 1.414 power. So again, just recall that last calculation. We're going to add a 1 in there, like so. 2.659. And the last one's 2 to the square root 2 power. Now that we can do as well. All we got to do is hit our 2, then our exponent button, and then we're going to put in a square root of 2. And here you can actually hit the right arrow key once. It's going to take you out from under that square root. Hit it again and you'll jump down now to where you're back at the base. And hit enter. You get 2.665. Alright, so that's all that is, just making sure we know how to get those exponents punched into the calculator. Going back real quick and talking about jumping down out of that exponent again. Let's say if we were to do like 2 to the 3rd power. Okay, we know that's 8, right? So if we wanted to do 2 to the 3rd power plus 2, like say we wanted to add 2 to it, you should get 10, right? Well, a mistake a lot of people make if your calculator sets up like this, you forget to jump down out of that exponent. If we wanted to do, again, we're looking at, you know, what is 2 cubed plus 2? Okay, should get 10, right? Well, if you forget to jump down out of the exponent and just put plus 2, well, now that's not 10, it's 32, right? Because it did 3 plus 2 is 5, 2 to the 5th is 32. Again, you got to make sure that you jump over and then do your plus 2. And so notice the difference between those two expressions. The 2 here, plus 2 is big, here it's kind of small. It's a really small difference there, but it does make a difference in the calculation. So just make sure you do that. Don't accidentally stay up in that exponent and end up with a wrong calculation. All right, as we're talking about exponents, one thing that we're going to need as we get into this section is the laws of exponents, and these you should remember hopefully from previous algebra course. If you need some help with these, I'll post some materials alongside this video just to go over what are all these laws of exponents and how do they work. Don't want to take time right now to do that, but there will be another video posted. But just know that we'll be needing these properties of exponents later on when we start looking at solving some equations with exponential functions. All right, so let's get to the actual definition of the exponential function. And this is the basic form of an exponential function. The book actually has a different sort of definition. The book has f of x equals c a to the x, where this is a constant. But really the key to this function is, notice where the variable x is. It's in the exponent, right? A raised to the x power. Now we've had functions before with exponents in them, something like maybe f of x equals x squared. That has an exponent in it, but notice that the variable is not in the exponent, it's down in the base. Here, if it's an exponential function, that means the variable is in the exponent, a raised to the x power. And there's some restrictions on that variable a. It's a real number, a greater than 0 and not equal to 1. And we'll kind of talk about that here in just a minute as well. But that's our exponential function. So some examples of what this might look like. Maybe f of x equals 2 to the x is an exponential function, or f of x equals 1.4 to the 2x could be an exponential function, or 0.5 to the x. The key there again is the variable x is in the exponent. All right, so we're going to look at some graphs of some exponential functions here and just get a feel for what this function looks like and kind of how it works. And so I'm pulling up the calculator, and we're going to start out graphing f of x equals 2 to the x. It looks just like that. And checking my window here, just using the standard window from -10 to 10 on the x and y axis. And my graph looks something like this. Okay. And so you'll notice this curved line here is our function. And it looks like it disappears down here. Now actually what's happening here at that x-axis, if I turn off the axis here to where it doesn't show the x and y axis, notice that graph doesn't disappear. Okay, it kind of flattens out as it gets close to where that x-axis is. Okay, but just wanted to show you that graph doesn't disappear. It does continue really close to that x-axis. But that's the basic shape. Flattens out here on the left, and then it really kind of takes off as you get further to the right. And so that's 2 to the x. And if you think about these points here, if I were to just sketch a quick picture of what we're dealing with. Kind of know what the picture looks like, but a lot of times it's good to think about what these points actually are. So if we do like f of 0, 2 raised to the 0 power is 1, right? Anything raised to the 0 power is 1. So maybe that's right here at 1. If we do f of 1, 2 to the first power is 2. So an x value of 1 gives us a y value of 2. If we do f of 3, I'm sorry, let's do f of 2. 2 squared is 2. I'm sorry, 2 squared is 4, right? 2 times 2. So now we're up here at 4. And if we do f of 3, 2 cubed is 2 times 2 times 2 is 8. And then if we do f of 4, you kind of notice a pattern. Every time we increase that x value by 1, we're multiplying by 2 again, right? So it doubles. So f of 3 is kind of way up here at 8, and then f of 4 is going to be really off the screen. You know, as that x value increases, that y value really gets out of control. F of 5, double it again, you get 32. Double it again for f of 6 is 64, and so on. Now, on the other side, if we do f of negative 1, that's 2 to the negative 1 power, and this is where we get into those properties of exponents. A negative 1 power, if you'll recall, we can simplify that by flipping it, right? It's like a reciprocal. So 2 to the negative 1 is really the same as 1/2. So 1/2 f of negative 2, 2 to the negative 2 power. Again, flip it over. You get 1 over 2 squared, which is a fourth. One over 4. So now it kind of gets really cut in half again. And there's a pattern there where if you do f of negative 3, it gets cut in half again. It was a half, a fourth, and now it's going to be an eighth. So it gets, again, closer and closer to the x-axis there. And if you were to connect these, you'll notice that's essentially the picture we got on the graph, right? If you go back and look at this picture right here, you see that that makes sense now looking at, whoops, sorry, looking at the picture there that we sketched. So exponential functions have this sort of behavior where because you're multiplying, and it, in this case, 2 to the x doubles and doubles and doubles over and over, it really grows quickly, and that's where you've probably heard the phrase exponential growth before. It's kind of what we're dealing with here, and we'll talk more about that in just a little bit. But that's 2 to the x. And looking at this picture right here, again, that thought of exponential growth, you've probably heard that phrase a lot, and that's what this graph below is. Anytime you do a population growth, a lot of times it's exponential growth. And this chart is number of cell phone subscribers at the end of each year. Starting in 1985 and increasing to 2004, you notice it's got that same sort of picture. It starts out kind of small, not much growth in kind of this region, but eventually it sort of picks up steam, and there's an updated graphic in your book of this, and it really continues to pick up, you know, from there. And so exponential growth, you see it in population growth, a lot of different places that you see that. So, all right, so there's some properties of the exponential function 2 to the x here. The domain is a set of all real numbers. 2 to the x, you can plug in any value for x there and it works. There's no x-intercepts. The y-intercept is 1. We can kind of see that. There is a horizontal asymptote as x goes to negative infinity. And that's, again, this behavior where it gets closer and closer to the x-axis without touching or crossing the x-axis. It's increasing. It's 1 to 1. There's a few more properties there. Really, these aren't that important as we're working and doing some of the work in the homework. So don't sweat, you know, about this stuff right here. Now that function we just looked at, 2 to the x, that 2 was that value of a, right? So the next question, well, what happens if a is something different? What if it's between 0 and 1? Say f of x is 1/2 to the x. So now this value of a instead of 2 is 1/2. What's going to change there? So if we punch that in, go down here and put 1/2 to the x, and take a look at the graph there. Looks similar. And let me turn off 2 to the x here and just look. This is 1/2 to the x. Very similar, right? But kind of flipped around. We get that reflection on the y-axis is kind of what happens there. And so what's causing that to happen? Well, if we look at some function values here, just to run through a few of these, f of 2, f of 3, this should be enough to kind of pick up on the pattern. So 1/2 to the 0 power, of course, is just 1, right? Anything to the 0 power is 1. 1/2 to the first power is 1/2. Now what's 1/2 squared? 1/2 times 1/2 is 1/4. Notice how it got cut in half each time we increase that x value. So if we do 1/2 cubed, we would expect it to get cut in half again. 1/2 of 1/4 is 1/8, right? And you can get this kind of the same way if we do 1/2 cubed is 1 cubed over 2 cubed. Bring down that exponent into both of those, and that's that 1/8. Same idea there. But either way, you notice as that x value increases, it gets cut in half every time, which is what we see on that right-hand side of the graph, where it gets cut in half each time we increase. It gets closer and closer to that x-axis. But think about it: if you keep cutting it in half, it's never going to get to 0, right? It's going to get closer and closer and closer to the x-axis, never get to 0. And so that's why we said just a second ago there's an asymptote there as x gets higher, in this case, gets closer to the x-axis. Now if you go the other way with it, say -1, -2, and -3, that's 1/2 to the -1. Remember, we said that's basically a reciprocal. So that becomes 2/1, which is 2. So we get 1/2 to the -2. That's 2/1 squared, which is 2 squared over 1 squared. That's 4. And you can probably see a pattern. From 0 to -1, it went from 1 to 2, and doubled. From -1 to -2, it doubled. So from -2 to -3, it's going to double again, and we're going to get 8. Okay, and so as you get further into those negative x values, it's doubling and increasing higher and higher. Okay, and so that's what happens if you choose a different value for that base 1/2. In this case, it kind of turns the graph around. Now, if you continue to change that, the key here is 1/2 is between 0 and 1. So if we did like 0.1 to the x, something that's smaller and closer to 0, what's that graph look like? Notice it's really, I don't know if you can see that, it's very, very steep right there, and then comes down and gets closer to the x-axis again. If we were to do something like 0.9 to the x, something that's closer to 1. Again, 1 is kind of that breakover point for that graph. 0.9 to the x is really a lot flatter. See that? Kind of the way it decreases there. And so as you change that base, it really does change the kind of the steepness of your graph. The closer to 0 you get, the steeper that graph is. And then the closer to 1 you get, the flatter that graph is. I guess really the better way to say it is the further from 1 you get, the steeper your graph gets. And we can kind of see that as well if we go back and look at, like we had 2 to the x. I'm going to graph a couple more here. We could do like 4 to the x. Let's do something really close to 1, like 1.1 to the x. And so starting with 2 to the x, looks like this. That's one we saw a second ago. Here's 4 to the x, a lot steeper, and then 1.1 to the x, not really very steep at all, right? So with these exponential functions, again, the closer to 1 you get with that base, the flatter it gets, the further from 1, the steeper it gets. And that's kind of the rule of thumb there for those exponential functions. Okay. Again, there's some notes here about some properties of that function. I would say really don't worry about those.